anyone else here? Hello, everyone. Just give me a second. I'm just writing down the topic of today. So the goal of today's lecture is we're going to be covering the hypergeometric distribution. So hopefully everyone had enjoyable reading week. Again, this is MAE 209, Probability and Statistics. And my name is Richard Kohar. Okay. Excellent. So everyone can hear me loud and clear. So that's what we're going to be doing. We're going to be trying to cover the hypergeometric distribution. There was one example that I wanted to cover from our last lecture, which was about the binomial distribution. And since we have a lot of students that are in aerospace design, aerospace engineering, I thought this was an interesting example that we could use. So we're going to suppose that an airplane will fail when in flight with probability 1 minus p independently from engine to engine. And then we suppose further an airplane will make a successful flight if at least 50% of its engines remain operative. What values of P is a 4-engine airplane preferable to a 2-engine airplane? Oh, I see some couple of questions. When can we expect the midterm to be marked in entirely? Soon. I have to finish it up tonight. Yeah, when will we get the marks back? Yes, soon. What is the plan for the class for the rest of the semester? Are we staying online or going hybrid or full in person potentially? So the goal is to stay probably hybrid with lectures being done over online and in testing person. That's the goal. When will all the midterm questions be marked? Okay, yes, those will soon be marked as well. Does that answer those questions in the chat? Okay. Perfect. Okay, perfect. Yeah, I just need some confirmation. I can't see anyone, agreeing or shaking their head yes or no. So again, I need some... if tests are in person, will they be open? That is a good question. It's more likely that the test will be closed book then, if they're in person. So the material that will start from today and carry on to the next term, that's the material that will be tested on the next midterm. So I would say that this is a good time to start preparing and studying in a way that it will be a closed book. And the hypergeometric distribution is covered in section 3.5 in the textbook. Will there be any given formula sheets or anything? I have to discuss that with the other section. So as for formula sheets, we'll have to discuss that. Okay? Because whatever I do, the other section will do, and vice versa. Okay, so what we can do then to examine this example here, where we have a 2-plane and a 4-engine and a 2-engine plane, and we have to figure out what values of P, what we'll do is we'll let we'll have a random variable that is binomially distributed. We'll say that there's 4, and there's a certain success of p. Again, that's where p is probability of success. So it doesn't fail. And then we'll create another variable too. So this will be the 4-engine airplane, and there's the 2-engine airplane. So the probability that a 4-engine plane makes a successful flight. So what we need to do is we need to calculate the probability that it's 2 engines survive. So again, at least 50% of the engines remain operative. So we'll say that 2 of the 4 survive, 3 survive, and 4. So doing that, we have 4 choose 2 times p squared times the complement of that, plus we'll have 4 choose 3 p cubed, and then its complement 1 minus p, plus 4 choose 4, that's p to the 4th, and 1 minus p to the 0. So we can calculate 4 choose 2. So that's 6p squared, 1 minus p squared, plus 4p cubed, plus, and then 4 choose 4. There's only one way to do that, so that's 4 p to the 4th. And similarly, we can do the same thing with the probability for the 2-engine plane. So for the 2-engine plane, well, we can have it where there's 1 engine or 2. So I can have 2 choose 1. So I can pick one of the engines that survives, plus all 2 survive, that's p squared. So simplifying that, 2p, 1 minus p, plus, well, actually I'm just calculating the coefficients here. Okay. So we want to know when the 4-engine is preferable to the 2-engine. So we can say then, therefore, the 4-engine plane is safer if, so we can take our criteria here that we have for the 4-engine, and we'll say that it's greater than or equal to the 2-engine. So that would be 2p, 1 minus p. Okay. So if we divide by p on both sides, what I'm left with is then 6p, 1 minus p squared, plus 4p squared plus p cubed, 2 times 1 minus p plus p squared. Right. And expanding that out. Okay. So what really we're doing now is just, it's algebra. Okay, so we can expand out that 1 minus p squared. And bringing the minus, the 2 minus p over to the one side. So at this point, it's just being very careful about tracking all my terms. Minus 8p squared, and I have the 7p. Okay. And factoring this, again, here's a cubic, so there's a couple of ways that you could do this. You could plug it into your favorite computer algebra system. You could use long division. Any of those will work. Okay, so this reduces it down to this. And if I set this equal to 0, basically I get p is greater than or equal to 1, so I can't really use that term. It doesn't make any sense. So I'm left with this linear term. Okay, so that means that the 4-engine plane is safer if the engine success probability is at least 2/3. So a 4-engine plane is safer if the probability of success is greater than 2/3, and the 2-engine plane is safer. So, is everyone okay with that so far? Any questions? Just looking over at the chat. Okay. Yes, but the answer does not feel like it should be right. It feels counterintuitive. Math doesn't care about feelings. Yeah, sometimes it can be counterintuitive. So there's some, you can chalk this up maybe to the law of diminishing returns. But this is just an example. Now, again, there's some, like everything, there is built-in assumptions. There's assuming that the engines are all the same. So if I had 4 of the same engines used in one plane and 2 of the same plane engines used in that same plane. So again, it's not like 4 engine planes usually have the same engine. What it's saying is again, you have to make sure that we go back to the probability. So again, it's the probability of success. Right? So each plane has to, oops. Again, it's the engine itself. So again, it's 1 minus p independently from engine to engine. So, this is not always the case too. Again, independent is a strong assumption. Perhaps that the engine is drawn from the same batch. If it's from the same batch, it's, again, if we have more information about things, we can adjust this. But just given this, that it's independent and it will be successful with p, or 1 minus p it fails, this is what we get. Like I said, you have to go back to your assumptions. If your assumptions fail, then you can't use this conclusion then. You can also, there's a similar example, I think example in the textbook. Example 3.3 talks about electronics manufacturer. Electronics manufacturer. So that's probably a good one to read through as well. Okay, so now we can get into the hypergeometric distribution. So this is the example, or the motivating example. Okay, so what is the probability distribution for the number of hearts dealt from a deck of well-shuffled cards if 4 cards are dealt. Okay, so again, making sure that we know what a deck of cards looks like. There's our deck, well shuffled. And we're going to pick out hearts. So that's what we call a heart. Now, there's some assumptions that we're doing here. When we are dealt from a well-shuffled deck of cards, we're picking one card. Here's another card. You notice that I'm not putting them back into the deck. And that's what we're sampling without replacement. So I'm just going to make this little note, without replacement. Usually that's how cards are dealt, without replacement, but there could be cases where you pick a card and then you put it back into the deck, and you pick another card and you put it back in, and you could pick the same card again perhaps. So that's called with replacement. So this one is without replacement. So what we want is the probability distribution. So let X be the number of hearts in 4 cards. Okay, so in this case, this is saying that I have 0 hearts. So what I'm going to say here is there's 13 hearts in the deck, and I'm going to pick 0 of them. There remains then 52 minus 13. And I'm going to pick all 4 of those cards then would be not hearts. So that would be choose 4. And in the denominator, the number of ways that I can make a 4-card hand is, there's 52 cards, and I'm going to pick 4 of them. So this would be the number that we have for 0 hearts in a 4-hand, like a 4-card hand. Okay, if there's 1 card that's a heart, that means that there was 13 cards, and from that there was 1 that we picked, and 52 minus 13 is 39. So there was not 4 cards that were non-hearts, but now there's 3. Can you see the pattern yet? So for 2, there's 13, choose 2. There's 39 non-heart cards, and 2 of those then would be selected out of, and then in the bottom, out of all the possible 4-hand cards, again, it's still 52, choose 4. And just finishing this up for completeness. Choose 39, choose 0. Out of the 52, choose 4. Okay. So this is all the possible ways. Move these deck of cards out of the way. So we can calculate each of these, but what I would like to do is, the original question says, what is the probability distribution for this? And so what we can see here is we can generalize that. So I'll write this with maybe a different color pen. Let's use blue. So we're going to say that, just for a general There's my capital X, and there's the little x. We know that this number is not changing. We have 13, so there's always going to be 13, and that's the number of successes. So we have the number of hearts. That's what we want, and it's not 0 in this case because we were trying to have that as a variable, so we want to have not 0, but x. Up here, it's going to be 39, and in this case, there's 4 of them, and we're decreasing each time we go up by a success. So we're going to do 4 minus x all over 52, choose 4. And that's the probability distribution equation for that. So what's nice now is that we have this general formula. I can punch this into, say, a calculator, like a Casio, and I'll do 13 choose, and I'll use a variable x times 39 choose, and let's do 4 minus x, and we're going to divide it by 52 choose 4. So punch in 0, and so this is what we get for calculating this one right here. So that is equal to 0.30, and let's do 4. We'll do 1. 2. 3. And lastly 4. A very small number. 0.0. Let's do roughly 3. Okay. And we can also check to make sure that this is a proper probability distribution, because we need to make sure that it sums up to give us 1. It might not add up to, oh, it does add up to 1 nicely. But it's possible that it might not have worked out nicely because of rounding error. And if you wanted to see kind of what the probability distribution should look like, of course I smudged it. Let's say 1, 2, 5. So roughly around here, we'll say there's 0. Over here is 4, so let's do, say, 2.1. Three is quite small. So over here. And that's the graph of the probability distribution. So again, this is a situation that can pop up from time to time. And so we kind of formalize it. We've got we have sampling without replacement. We've got successes and we have failures. And let's generalize that then. Kind of how we did it with the binomial distribution. So here we go. So let's generalize. So we suppose that there are, let's say there are n outcomes, kind of like how we had the 52 cards. Okay, and from there we're going to have m, we'll call those successes. So when we flip back to our previous one, we have, in this case, we're looking for the number of hearts, and that's what we would have called our success. And then the complement of that, so n minus m, those are our failures. So if we were drawing cards, this isn't what we wanted. We wanted to have the number of hearts. So we have successes, we have failures. Okay. And this is following the same notation as what's in the textbook. They make a difference between n and little n. So they have capital N for the outcomes, and then they say if there are little n, so little n trials. So when we were looking at this, we had 52 outcomes, which were the cards, and we had 4 cards, which are like the trials. So is this a generalization for a hypergeometric distribution as compared to binomial distribution? No, it's not. It's not quite the same situation. Again, it's a situation that has come up time and time again, and it comes up so frequently that we have these equations to describe the situation. So there are some assumptions that we made, like in the binomial distribution, we had those 3 assumptions. Again, there's assumptions here in order for us to apply that model. So if there are n trials involving sampling without replacement, then the probability of x successes in n trials is given by, so this is, so I'll use a big capital X, this is the random variable, is equal to little x. So they have over here, so there's the number of totals or outcomes that are successes. Here's the M. So it's M, and we're going to choose X of those. The failures, which would be then N minus M. And in this case, just like how we did with the hearts, instead of 4 in this case, which was our number of trials, we're going to use the generic N, right? So the N trials. And we're going to subtract X of those. So here's our successes, the number of successes. Here, over here is the number of failures. And then over here, we have all the possible outcomes. So we had like the 52, and there was the number, so the number of outcomes, and then choose the number of trials. And that's the formula. Again, you could be freaked out if you saw this without any context, but just, again, I usually have some sort of prime example to help recall this, and something like the card example is something that helps me, help me remember this. So while there's like all these different letters and parameters, really it comes down to thinking like of a deck of cards. I have things I want, things I don't want, out of all the possibilities. Also, along with this, we have the expected value. So here we have, it's the number of trials times M over N. Now this is very similar to the binomial distribution, because the binomial distribution goes something like N times the probability of success. And this is very similar. So we have the N over N, which is the P, or the proportion of successes to the entire outcomes. So you can kind of see that there's a similarity to this. And the variance is equal to N minus N all over N minus 1 times N times M over N times 1 minus M over N. So again, we remember that when we were looking at the binomial distribution, we had N times P times the complement of P. So N times P times 1 minus P. And we see a similar thing here. We have N. Again, if we thought of this as P, the kind of proportion of successes to the total number of outcomes, we see that pops up here, and then 1 minus, and then there's our P again. So it's very similar. The only thing that happens in this case is we kind of have this correction factor. So there's the variance. So I want to do a quick example. Maybe I'll switch back to my black pen. And this example comes from zoology. So it's a very interesting zoological application where we can use the expectation of a hypergeometric distribution to estimate the size of an animal population by using a tagging system. So let's assume that there's 1,000 fish in a lake. Let's say it's in Ontario, not Lake Ontario, but just say a small lake in Ontario. And we're going to say that, and all of these were caught and tagged. And so they'll wait a couple of months, or let's just be generic and say after a while, a new catch. And let's say that they, instead of catching 1,000, they caught 500. So they caught 500 fish, were caught, and 60 of them had tags. And why is this happening? Because we have fish that we have caught, we tagged them, and then we allowed them to go back into the general population, intermingle. Maybe they have fish babies, and they have new fish growing, and so again, there's some time elapsed after we have this new sample of 500 fish. They say what conclusions can be made. Concerning the number of fish in the lake. So we have some information here. We know that there was 1,000 fish that were tagged in the lake. What we don't know is how many there were in total. So we can't really answer what n minus m was because we don't know what n was. But we do know that in this case we had a small sample. We said 500. And we're left with one piece of information left. We have 60. And we're going to say that that was the expected value. We're going to say that there was 60 fish that were caught. And that's the estimate of it. So these are tagged fish in the lake. Don't know. This is our number of So this is our number of untagged. This is our sample. And this is our expected value. So we can actually estimate then how many fish are in the lake. Because if we use the expected value is equal to n times m over n, substituting our values, we get 60 times 500 times 1,000 over n. And then solving for that, so that is our estimate. Which is interesting that we were able to, from a small sample of tagging, releasing it into the population, and then resampling again, we can kind of have an estimate of how many fish there are without explicitly counting every single one of them. Okay. Is there any other questions before we finish today's lecture? Could you explain how to identify the different variables? Which variables do you mean? Do you mean the variables m, n, and x? Is this what you mean? I'm just waiting for an answer to see what they... How do you know which numbers in a problem refer to which variable? Well, again, we can just, as you're reading the information, it's just basically what I'm doing here. But over here, what I could say here is, again, here is the m is the number of successes. So number of successful outcomes. N is the total number of outcomes. X is the number, so number of, let's say, total, and in this case X is the number of outcomes we want. To occur. And N is the number of trials. Okay. For those that are, you're welcome to leave. I'm just finishing up answering this question. So hopefully that will help kind of defining each of those letters. So in this case, I had I saw that this was the number of successes that I had. I had 1,000 fish that were tagged. This was something that I didn't know. And then when I was doing the resampling, we had the 500, so that's our number of trials again. So you can think of this as kind of before. We have the fish. And when I, randomly selected out of that 500 fish, I had 60. And in this case, we're assuming that that's the expected value. Okay. I hope that clarified the answer, the question. So, if there's any more questions, feel free to send me an email, or we can set up office hours. Again, send me an email through my RMC email address. And there's some questions posted for you to try in the textbook. And without any further questions, thank you and enjoy the rest of your day. Take care, everyone.